In the winter of 1610, the world was small. It was a place with Earth at its center. The sun, the moon, the planets, and all the stars revolved around us. This was not just a scientific model. It was a philosophical truth. It placed humanity at the heart of creation. On January 7th of that year, a man named Galileo Galilei pointed a new instrument, a telescope, at the planet Jupiter. He saw what he thought were three small, fixed stars near the planet. But he kept watching. Over the next few nights, he saw them move. And they were not moving independently. They were moving with Jupiter. He realized they were not stars at all. They were moons orbiting another world. This discovery, documented in his notes, did something profound. It was a crack in the foundation of the old world. If other planets had moons, then Earth was not unique. It was not the center of all motion. This simple observation, made with a tube of polished glass, forced a philosophical crisis. It suggested the universe was vastly larger and more complex than anyone had imagined. It suggested our place in it was not as special as we had believed. We were not the center. We were just one part of a much grander system. Today, we face a similar kind of philosophical edge. We have looked out into the cosmos and back to the very beginning of time. We have a story of the universe, the Big Bang. It says everything. All of space and time exploded from an infinitely dense point about 13.8 billion years ago. But this story has a problem. It starts with a miracle, a moment of creation from nothing that we cannot explain. It leaves us with a deep question. What came before the Big Bang? What is outside our universe? These questions feel as impossible as asking what was north of the North Pole. But a new idea, much like Galileo's observation, challenges our sense of place. It is a radical and strange idea. It suggests our universe is not the beginning and the end. It suggests our universe might be a bobby, born from a process that happens inside something else. That something else is a black hole. The theory proposes that when a massive star collapses under its own gravity, it creates a singularity, a point of infinite density. But instead of being an endpoint, that singularity could be the seed of a new universe. Our Big Bang might have been the result of a black hole forming in a parent universe. We might be living inside the creation of another cosmos. This idea, like the moons of Jupiter, forces us to reconsider everything. It changes our origin story. It suggests a vast, interconnected web of universes constantly being born. It means our beginning was not a unique event, but a natural cosmic process. We are not the center. We are just one branch on an infinite cosmic tree. Number 15, the Big Bang and black holes share the same impossible core. A star more than 20 times the mass of our sun will end its life by collapsing into a black hole. The escape velocity from its surface becomes greater than the speed of light, which is 299,792 kilometers per second. Nothing, not even light, can escape. In 1965, Roger Penrose proved that any object undergoing such a gravitational collapse must inevitably form a singularity. This is not a guess. It is a mathematical certainty under the rules of general relativity. The known laws of physics break down at this point. The entire observable universe, all 93 billion light-years of it, was once compressed into a space smaller than an atom. This initial state, the one that preceded the Big Bang, is also described as a singularity. Just like the center of a black hole, it was a point of infinite density and infinite temperature. All the matter and energy we see today was contained within it. The equations that describe the beginning of our universe and the center of a black hole look disturbingly similar. They both point to a place where our understanding of reality ceases to function. This is the first and most fundamental connection. The two most extreme objects known to physics, the origin of our cosmos and the endpoint of a massive star, are described by the same broken mathematics. General relativity, Einstein's theory of gravity, works perfectly for planets, stars, and galaxies. But when it confronts the infinite curvature of space-time in a singularity, it fails. The equations produce answers of infinity, which, in physics, is another way of saying we don't know. For decades, physicists treated these as two separate problems. The Big Bang singularity was a problem of cosmology. The black hole singularity was a problem of astrophysics, but what if they are not two problems? What if they are two sides of the same coin? This is the core of the baby universe hypothesis. It proposes that the singularity inside a black hole does not just sit there as a dead end. Instead, it bounces. The idea is that when matter is crushed to an unimaginable density, new physics takes over. As quantum effects, which are not included in general relativity, might become dominant. These quantum gravity effects could create a repulsive force, preventing a true infinite collapse. Instead of a singularity, the matter and energy rebound, creating an explosion of new space and time. This explosion would, from the inside, look exactly like a Big Bang. So, the formation of a black hole in a parent universe does not create a point of broken physics. It creates the starting conditions for a new universe. Our Big Bang was not a beginning from nothing. It was the result of a process that happened somewhere else in another cosmos. Our universe is the inside of a black hole. This solves a major philosophical headache. Science is about cause and effect, but the Big Bang, as a singular event from nothing, has no cause. It is a scientific creation myth. The baby universe theory provides a cause. The cause of our Big Bang was the collapse of a star in a parent universe. It turns the origin of our universe from a supernatural seeming event into a natural physical process. It also changes how we think about black holes. There are an estimated 100 million stellar mass black holes in our Milky Way galaxy alone. If even a fraction of these can spawn new universes, then the cosmos is incredibly fertile. The universes are constantly being born. Our existence is not a one-off fluke. It is a predictable outcome of the laws of physics operating on a cosmic scale. The parallel between the two singularities is more than just a mathematical curiosity. It is a signpost. It points toward a deeper connection, the place where our theory of gravity fails for large-scale cosmology is the same place it fails for the end of life of a single star. This coincidence is too strong to ignore. It suggests that the end of one thing is the beginning of another. The death of a massive star in one universe could be the birth of a new cosmos, complete with its own stars, galaxies, and perhaps its own life. Our universe's beginning looks just like the inside of a black hole, because that is exactly what it might be. Number 14, our universe appears suspiciously fine, tuned for life. The strength of gravity is determined by a number called the gravitational constant. Its value is approximately 6.674 times 1011 nm kg squared. If this number were slightly larger, stars would burn their fuel much faster. They would be hotter and more massive, but their lifespans would be too short for complex life to evolve on any orbiting planets. If the constant were slightly smaller, stars would not be hot enough to ignite nuclear fusion in their cores. The universe would be dark and cold, without the elements necessary for life. The cosmological constant is a term in Einstein's equations that represents the energy density of empty space. It is responsible for the accelerating expansion of the universe. Its observed value is tiny, about 10 to 1 squared in Planck units. If it were significantly larger, its repulsive force would have ripped the universe apart before galaxies, stars, and planets could ever form. If it were negative, the universe would have collapsed back on itself long ago. The physicist Leonard Susskind calculated that if this constant were different by even 1 part in 101 squared O, we would not be here. These are just two examples of what is known as the fine-tuning problem. The fundamental constants and initial conditions of our universe appear to be precisely balanced on a knife's edge for the existence of complex structures like stars, galaxies, and life. The strength of the electromagnetic force, the mass of the neutron compared to the proton, the initial amount of matter in the universe, dozens of such parameters seem to have values that are just right. Change any of them by a tiny fraction, and the universe becomes a sterile, uninteresting place. This has led some to conclude that the universe was designed by an intelligent creator. Others have proposed the anthropic principle, which states that we observe the universe to be this way simply because if it were any other way, we would not be here to observe it. This is true, but it is not a satisfying explanation. It is like a person surviving a firing squad of 100 marksmen and when asked how they survived, replying, "Well, if I hadn't, I wouldn't be here to answer you." It does not explain why all the marksmen missed. The baby universe hypothesis offers a third option, a physical explanation rooted in a concept similar to biological evolution. The idea is called cosmological natural selection, proposed by physicist Lee Smolin in the 1990s. It provides a mechanism for why the universe is so well suited for producing things like us. The theory works like this. When a black hole forms and creates a new baby universe, the fundamental constants in that new universe might be slightly different from the parents. There could be small random mutations in the laws of physics. Now, consider which kind of universe will have the most offspring. A universe that is good at making black holes will create more baby universes. What kind of universe is good at making black holes? A universe that is good at making massive stars. To make massive stars, you need a universe that can form large galaxies. You need gravity to be strong enough to pull matter together, but not so strong that it immediately collapses everything into one giant black hole. You need the forces that govern nuclear fusion to be balanced, so stars can live for billions of years, creating heavy elements in their cores. These heavy elements, like carbon and oxygen, are then scattered into space when the stars die, forming new stars and planets. It turns out that the physical constants that are good for making lots of massive stars are also the constants that are good for making life. Carbon, oxygen, and other heavy elements are the building blocks of planets and biology. Long-lived stars provide the stable energy sources needed for evolution. So, universes that are prolific in producing black holes are, as a side effect, also prolific in producing the conditions necessary for life. Under this model, there is no fine-tuning. Our universe has the constants it does because it is the descendant of a long line of universes that were successful at reproducing. Universes with constants that were not conducive to making black holes simply had fewer or no offspring. They were evolutionary dead ends. We find ourselves in a universe that is good for life because the universes that are good for life are the ones that dominate the multiverse. This elegant idea turns the fine-tuning problem from a philosophical mystery into a question of cosmic evolution. It does not require a designer or rely on the simple tautology of the anthropic principle. It suggests that the laws of nature are not static. They can evolve. Our universe is not a miracle. It is a product of a vast cosmic lineage shaped by a process of reproduction and selection, with black holes serving as the seeds of new generations. The reason the constants seem perfect for us is that the same constants are perfect for making more universes. Number 13, cosmic evolution selects for more black holes, not life. In Charles Darwin's theory of natural selection, the key to survival is not strength or intelligence, but reproductive fitness. The organisms that pass on their genes to the next generation are the ones whose traits become common. A peacock's elaborate tail is not good for flying or hiding from predators, but it is very good at attracting a mate. Its existence is explained not by its benefit to the individual's survival, but by its role in reproduction. Lee Smolin's theory of cosmological natural selection applies this same logic to the cosmos. The unit of selection is not an organism, but an entire universe. The method of reproduction is the formation of black holes. The key insight is that the theory does not select for universes that are good for life. It selects for universes that are good at making black holes. The fact that our universe is hospitable to life is a byproduct, not the primary goal of this cosmic evolution. Consider the process. A universe is born from a black hole. Its fundamental physical constants are slightly different from its parents. If these new constants make it easier to form massive stars that collapse into black holes, this new universe will have more children than its parent. If the constants make it harder to form black holes, it will have fewer or no children. Over countless generations of universes, the parameter space of physical constants will be explored. The universes that come to dominate the multiverse will be those whose constants are optimized for black hole production. Let's look at what that requires. To make a lot of black holes, you first need a lot of stars. Specifically, you need massive stars, those over 20 times the mass of our sun. To get these, you need a universe that is not uniform. It must have slight density variations in the early moments after the Big Bang. These variations, which we see in the cosmic microwave background radiation, are the seeds of galaxies. Gravity needs to be strong enough to pull these clouds of gas together to form galaxies, and then stars, but not so strong that the universe recollapses. You also need a lot of carbon and oxygen. These elements are not created in the Big Bang. They are forged in the cores of stars. Surprisingly, they also play a crucial role in the cooling of interstellar gas clouds. Without elements like carbon and oxygen, the gas clouds would be too hot to collapse and form stars. A universe rich in carbon is a universe rich in stars. A 2002 study by astrophysicist Fred Adams showed that changing the fundamental constants, even slightly, would dramatically reduce the amount of carbon and oxygen produced by stars, thus hindering the formation of future generations of stars. So, a universe optimized for making black holes is one that is large, long-lived, and filled with galaxies and stars that are efficient at producing heavy elements like carbon. This sounds very familiar. It sounds like our universe. The fact that these same conditions are also necessary for life behind. We are carbon-based life forms living on a rocky planet made of heavy elements, orbiting a stable star as a secondary consequence. This is a crucial distinction. The theory is not teleological. It is not aiming for us. We are just fortunate beneficiaries. The peacock's tail is for attracting mates, not for delighting human observers, though it does that too. Our universe's properties are for making black holes, not for making humans, though it did that too. This perspective solves a potential criticism of the fine-tuning argument. One could ask why the universe is not even more fine-tuned for life. Why is so much of it empty, cold, and hostile? If it was designed for us, it seems like a very inefficient design. But if the goal is to maximize black hole production, the design makes more sense. The vast empty spaces are necessary to allow galaxies to form without interfering with each other. The billions of years of cosmic history are needed for multiple generations of stars to enrich the universe with heavy elements. Smolin's theory makes a testable prediction. If the theory is correct, then any small change to the fundamental constants of our universe should make it less likely to produce black holes. Physicists can run simulations to test this. For example, they can model star formation in universes with a slightly stronger, weak nuclear force or a slightly different neutron mass. So far, many of these simulations suggest that our universe is indeed near a peak in the landscape of black hole production. Our set of physical laws appears to be very, very good at making black holes. This provides circumstantial evidence for the idea that our universe is a product of this cosmic evolutionary process. Number 12, a baby universe solves the black hole information paradox. In the 1970s, Stephen Hawking made a startling discovery. He combined the laws of general relativity with quantum mechanics and found that black holes are not completely black. They slowly emit a faint glow of radiation, now called Hawking radiation. This means that over immense timescales, black holes can evaporate and disappear completely. A solar mass black hole would take about 1067 years to evaporate. A supermassive black hole at the center of a galaxy could take 10100 years. But eventually they would be gone. This created a deep paradox. One of the fundamental principles of quantum mechanics is that information can never be truly destroyed. Information, in this context, means the specific quantum properties of every particle that ever existed. If you burn a book, you might think the information is gone. But in principle, if you could collect every single particle of ash, smoke, and heat, you could reconstruct the original book. The information is just scrambled, not erased. But what happens when something falls into a black hole? The object, with all its unique quantum information, crosses the event horizon and is lost forever. Then the black hole slowly evaporates. The Hawking radiation it emits is thermal, meaning it is random and carries almost no information about what fell in. When the black hole is completely gone, the information about the particles that formed it and fell into it seems to be gone too. It has been permanently erased from the universe. This is the black hole information paradox. It represents a fundamental clash between our two best theories of the universe, general relativity and quantum mechanics. One says the information must disappear, the other says it cannot. For decades, physicists have been trying to solve this puzzle. Leonard Susskind and Gerard and Hooft proposed the holographic principle, suggesting the information is stored on the two-dimensional event horizon of the black hole. But this is still a debated and incomplete idea. The baby universe hypothesis offers a radical but clean solution. The information is not destroyed. It is not stored on the event horizon. It is transferred to the new universe that forms inside the black hole. When a star collapses or an object falls past the event horizon, its matter and energy are crushed at the singularity. But instead of being annihilated, they become the raw material for a new Big Bang. The information is not lost, it is passed on. The quantum state of the matter falling into the parent black hole sets the initial conditions for the baby universe. This provides a physical mechanism for preserving information and upholding the laws of quantum mechanics. It is no longer a paradox. The black hole does not erase information from existence, it simply moves it to a new space-time that is causally disconnected from our own. From our perspective in the parent universe, the information is gone forever. We can never access that baby universe. But from the perspective of the multiverse as a whole, the information is conserved. It has just moved to a new location. The black hole acts as a one-way door, not an incinerator. This also has implications for the nature of our own universe. If our universe was born from a black hole, then the information content of our universe, all the particles, all the energy, all their specific properties guidelines, was inherited from the matter that fell into our parent black hole. The total amount of matter and energy in our universe is vast. The number of baryons, protons, and neutrons is estimated to be around 1080. This implies that the black hole that created our universe was incredibly massive. The baby universe idea reframes the information paradox completely. It is not a conflict between two theories. It is a misunderstanding of what a black hole is. A black hole is not an endpoint of matter. It is a gateway. It is the mechanism by which the universe recycles itself, preserving the fundamental laws of physics while creating new arenas for cosmic evolution to play out. The information that falls into a black hole is not lost. It becomes the seed of a new reality. Number 11, the arrow of time points away from a beginning we don't understand. We experience time in only one direction. We remember the past, but not the future. Eggs break, but they do not unbreak. Milk mixes into coffee, but it does not spontaneously separate out again. This one-way flow of time is one of the deepest mysteries in physics. The fundamental laws of physics, whether Newton's laws, relativity, or quantum mechanics, are time symmetric. They work just as well forwards as they do backwards. A video of planets orbiting a star would look perfectly normal if played in reverse, but a video of an egg breaking would not. The scientific explanation for the arrow of time is the second law of thermodynamics. It states that in a closed system, entropy, a measure of disorder or randomness, always tends to increase. The universe as a whole is a closed system. The reason time moves forward is that the universe started in a state of incredibly low entropy. The Big Bang was a moment of maximum order. All the matter and energy in the cosmos was compressed into a tiny, hot, uniform state. Since then, the universe has been expanding, cooling, and becoming more disordered. Stars form, burn out, and galaxies drift apart. The universe is constantly moving towards a state of maximum entropy, known as the heat death of the universe. The arrow of time is simply the universe progressing from its highly ordered past to its more disordered future. But this just pushes the question back one step. Why was the early universe in such a special low entropy state? This is a major puzzle in cosmology. Given all the possible ways the universe could have begun, a highly ordered state is statistically infinitesimal. It is like finding a deck of cards perfectly arranged by suit and number after a shuffle. It is so unlikely that it demands an explanation. The baby universe theory provides a natural explanation for this low entropy beginning. A new universe is not born from a random fluctuation of nothingness. It is born from the collapse of matter inside a black hole. The process of forming a black hole and then a new universe naturally resets the entropy. Think of the matter falling into a black hole in the parent universe. It could be a star, a gas cloud, or a planet. It is a relatively high entropy disordered system. As it is crushed toward the singularity, it is smoothed out and compressed into a hot, dense, uniform state. This process effectively erases the previous structure and disorder. The state of matter at the bounce that creates the new Big Bang is, by its very nature, a low entropy state. The initial conditions of our universe were not a random fluke. They were a direct consequence of the physical process that created it. The high degree of order was built into the birth mechanism. Our universe started with low entropy because it was born from a process that squashes matter into a simple, ordered configuration before it expands again. This creates a consistent arrow of time across generations of universes. A parent universe evolves towards higher entropy. At some point, some of its matter collapses into a black hole. This black hole creates a baby universe which starts in a low entropy state. That baby universe then evolves towards higher entropy, creating its own arrow of time. The process can repeat indefinitely. Without this explanation, the low entropy of the Big Bang seems like a miracle, a special condition that was just put in place at the beginning for no reason. It requires fine-tuning of the initial state of the cosmos, but the baby universe model makes it an automatic and necessary feature of cosmic reproduction. Each new universe is born with a clean slate, a highly ordered state from which complexity and disorder can grow. The arrow of time in our universe points forward because it points away from the moment of our birth, a moment whose orderly nature was determined by the physics of our parents' black hole. Number 10, the math inside a black hole can create a new universe. Einstein's theory of general relativity is the foundation of our understanding of gravity. It is this theory that predicts the formation of singularities at the center of black holes and at the beginning of the Big Bang. But general relativity is incomplete. It does not include the effects of quantum mechanics. Specifically, it does not account for a property of fundamental particles called spin. In the 1920s, a physicist named Élie Cartan developed an extension of general relativity that did include quantum spin. His theory, now known as Einstein-Cartan theory, did not gain much traction for many years because the effects of spin are usually incredibly tiny, only becoming significant at densities far beyond anything we can create or observe. The density required is the Planck density, approximately 5.1 times 1096 kilograms per cubic meter. This is a number so large it is almost meaningless. To get a sense of it, if you compress the entire observable universe into the size of a single atomic nucleus, you would still be far from reaching the Planck density. There is only one place where such densities might actually occur at the singularity of a black hole or in the initial moment of the Big Bang. Physicists Nikodem Poplavsky and others have explored the implications of Einstein-Cartan theory in these extreme environments. What they found is remarkable. In this theory, the spin of matter particles interacts with the fabric of space-time itself. This interaction creates a tiny repulsive force called the spin torsion. Under normal conditions, this force is negligible compared to gravity. But at Planck level densities, the spin torsion force becomes incredibly powerful. It acts as a form of anti-gravity, pushing matter apart. So according to Einstein-Cartan theory, when a massive star collapses to form a black hole, it does not form a true singularity of infinite density. As the matter gets squeezed to the Planck density, the repulsive spin torsion force grows astronomically, halting the collapse. The matter then rebounds violently in an event sometimes called the Big Bounce. This bounce creates a new expanding region of space-time, but it is a region that is causally disconnected from the parent universe. It exists on the other side of the black hole's event horizon. From the inside, this rapidly expanding, hot, dense region of new space-time would be indistinguishable from a Big Bang. The math works out, the theory avoids the singularity, the point where physics breaks down. It replaces the infinite point with a finite, though extreme physical event. The formation of a black hole becomes the mechanism for a cosmic bounce. This is not just a philosophical idea, it is a mathematical outcome of a more complete theory of gravity. Other theories of quantum gravity also suggest similar bounce scenarios. Loop quantum gravity, for instance, a competitor to string theory, also predicts that space-time is not a smooth continuum, but is made of discrete quantized loops. In this framework, there is a minimum possible size. You cannot squeeze space down to a true point. As a black hole collapses, the matter hits this fundamental minimum size and rebounds, creating a new universe. These theories provide a physical, mathematical basis for the baby universe hypothesis. They show that the singularity, the problem at the heart of both black holes and the Big Bang, might simply be an artifact of an incomplete theory. A more complete theory that incorporates quantum effects naturally replaces the singularity with a bridge to a new cosmos. This means the birth of our universe was not a violation of the laws of physics. It was a consequence of them. The extreme gravity and quantum effects inside a black hole in a parent universe provided the engine for our own creation. The equations themselves suggest that black holes are not cosmic prisons, but cosmic wombs. The mathematics that once pointed to an impossible infinity now points to an endless cycle of creation. Number 9, the horizon problem disappears if we all came from the same place. When we look out at the universe, we can see light that has been traveling for nearly 13.8 billion years. This light comes from the most distant regions of the observable universe. The surface from which this ancient light originates is called the cosmic microwave background, CMB. It is the afterglow of the Big Bang, a snapshot of the universe when it was only about 380,000 years old. One of the most striking features of the CMB is its incredible uniformity. The temperature of the CMB is the same in every direction we look, to a precision of about 1 part in 100,000. It is about 2.725 Kelvin everywhere. This presents a major puzzle known as the horizon problem. Consider 2 points on opposite sides of the sky in the CMB. The light from these 2 points is just now reaching us. That means they have never been in causal contact with each other. Information limited by the speed of light has not had time to travel from one point to the other in the entire history of the universe. They are outside each other's cosmological horizon. So how do they know to be at the exact same temperature? So it is like walking into a massive room and finding 2 people on opposite sides who have never met or communicated wearing the exact same obscure custom-made outfit. It is incredibly unlikely to be a coincidence. The most logical explanation is that they were given their instructions or their outfits at an earlier time when they were in the same place. The standard solution to the horizon problem is a theory called cosmic inflation. It proposes that in the first fraction of a second after the Big Bang, the universe underwent a period of hyper-accelerated expansion, growing exponentially in size. Before this inflation happened, the entire observable universe was a tiny subatomic region where everything was in causal contact and could reach a uniform temperature. Inflation then stretched this small uniform patch to an enormous size, preserving the uniformity on a grand scale. Inflation is a powerful idea and has become a standard part of the cosmological model. However, it requires the existence of a new hypothetical energy field, the inflaton field, with very specific properties. We have no direct evidence that this field exists. The baby universe hypothesis offers a simpler, more direct solution to the horizon problem without the need for an ad hoc inflaton field. You know, if our universe was born from the collapse of matter inside a black hole, then all the matter and energy that would eventually become our observable universe was once squeezed together into a single compact region. Before the bounce that triggered our Big Bang, all the material was, by definition, in the same place. It was all part of the same collapsing star or region of matter in the parent universe. It had ample time to interact and reach a state of thermal equilibrium, a uniform temperature. The bounce then initiated the expansion, and this inherent uniformity was carried along with it. The reason opposite sides of our sky look the same is because they originated from the same causally connected source. The uniformity of the CMB is a relic of its pre-Big Bang state when it was all compressed together inside our parent black hole. The problem disappears because there is no horizon to begin with. Everything we see was once in contact. This is arguably a more elegant explanation than inflation. It does not require inventing new fields or new physics. It uses the known physics of gravity and matter extended into the quantum realm to explain a fundamental feature of our cosmos. The universe is uniform because it was born from a single unified source. The baby universe model naturally produces the starting conditions that we observe, solving the horizon problem at its root. Number 8. The universe's flatness is a natural outcome of being born in a black hole. The geometry of spacetime on a cosmic scale can take one of three forms. It can be closed, like the surface of a sphere, in which case if you traveled in a straight line for long enough, you would end up back where you started. It can be open, like the surface of a saddle curving outwards, or it can be flat, like a sheet of paper obeying the rules of Euclidean geometry. Which geometry our universe has depends on its total density of matter and energy. If the density is above a certain critical density, the universe is closed. If it is below, it is open. So if it is exactly equal to the critical density, the universe is flat. You know, all of our measurements, particularly from the cosmic microwave background, indicate that our universe is incredibly close to being perfectly flat. This is another major puzzle known as the flatness problem. The state of perfect flatness is an unstable equilibrium point. If the early universe had a density that was even slightly different from the critical density, that deviation would have grown exponentially over the 13.8 billion years of cosmic expansion. For the universe to be as flat as we observe it today, its density in the first second after the Big Bang must have been fine-tuned to the critical density to an accuracy of 1 part in 106 squared. This is an astonishing level of precision. It is like balancing a pencil on its tip and having it remain standing for billions of years. It seems impossible that the universe would have started with this exact value by chance. The theory of cosmic inflation also provides a solution to this problem. The rapid exponential expansion of inflation would have stretched any initial curvature of the universe to such a vast scale that our observable patch would appear perfectly flat. It is like an ant living on the surface of a giant balloon. The balloon is curved, but from the ant's perspective, its local patch of the surface looks completely flat. The baby universe hypothesis again offers a different and perhaps more fundamental explanation. The geometry of the interior of a black hole is described by the Schwarzschild metric. A key feature of this geometry is how space and time behave. As an object approaches the singularity, the spatial dimension pointing towards the singularity effectively becomes time-like, and the time dimension becomes space-like. This is a strange and non-intuitive feature of general relativity. Some mathematical models of a universe forming inside a black hole, particularly those developed by physicists like E.I. Gendelman and D. Singleton, show that the newly created spacetime would naturally be spatially flat. The dynamics of the collapse and bounce process itself can produce a universe with a density that is extremely close to the critical density. The flatness is not a coincidence or the result of a separate process like inflation. It is a direct consequence of the geometry of the black hole from which it was born. The mathematical structure of the bridge connecting the parent universe to the baby universe, known as an Einstein-Rosen bridge or wormhole, imposes conditions on the new universe. And one of these conditions is that it must be spatially flat. Therefore, we do not need to fine-tune the initial conditions to an absurd precision. The flatness of our universe is a generic prediction of it being born inside a black hole. It is an inherited trait. Just as a child inherits genetic traits from a parent, a baby universe can inherit geometric properties from the black hole that created it. This, again, provides a solution that is baked into the model itself rather than requiring an extra mechanism like inflation. The flatness problem, like the horizon problem, ceases to be a problem. It becomes a natural and expected feature of a universe born in this way. The reason our universe is not a chaotic, curved mess is that the very process of its birth inside a black hole ensures a smooth, flat beginning. Number 7, the mass of our universe is what you'd expect if it were a black hole. How much does the universe weigh? It is a strange question, but one we can estimate. By adding up all the matter, both normal and dark matter, and all the energy, including dark energy, within the observable universe, scientists have arrived at a number for its total mass energy. The current estimate for the mass of the matter alone is around 1.5x 1053 kilograms. Now, let's ask a different question. For any given mass, there is a specific radius at which, if you compressed all that mass within it, it would become a black hole. This is called the Schwarzschild radius. The formula is simple. It depends on the mass and the gravitational constant. We can calculate the Schwarzschild radius for the mass of our own universe. When you plug the estimated mass of our observable universe into the Schwarzschild radius equation, you get a startling answer. You get a radius of approximately 13.8 billion light years. This number should sound familiar. It is the approximate radius of our observable universe. Let this sink in. The radius of our universe is almost exactly its own Schwarzschild radius. This means that the average density of our universe is incredibly close to the critical density required to make it a black hole of its own size. This is just another way of stating the flatness problem, but it frames it in a very provocative way. We appear to be living inside an object that has the precise characteristics of a black hole. This is a stunning coincidence if our universe is just a random explosion out of nothing. Why would the total amount of mass energy in the Big Bang happen to be the exact amount needed to make its eventual size equal to its own Schwarzschild radius? There is no reason for this in the standard cosmological model. It is another one of the just so features that we are forced to accept. But in the baby universe model, this is not a coincidence at all. It is a defining feature. If our universe was born from a black hole, then it is, by definition, an object whose mass and radius are related in this specific way. The event horizon of the parent black hole becomes the cosmological horizon of our new universe. This idea was explored by physicist Rajendra Gupta, who calculated that if our universe was a black hole, its properties would align closely with our observations. It provides a framework where the universe's overall size and mass are not arbitrary initial conditions, but are linked by the fundamental physics of black holes. This concept also helps to visualize what it means to be inside a black hole. It does not mean we are in a small, dark, crushed space. The interior of a black hole of this cosmic scale would be vast and dynamic. To an observer inside, it would not feel like a prison. It would look like an expanding universe. Space-time inside is so warped that all directions point away from the singularity, or the bounce, which lies in our past. The expansion of the universe is, in this model, the continued unfolding of space-time within this cosmic scale event horizon. The fact that our universe's mass and radius match the black hole equation is perhaps one of the most direct, albeit circumstantial, pieces of evidence for the theory. It takes what appears to be a bizarre, fine-tuned coincidence in the standard model and reveals it as a logical necessity. We live in a universe that looks like a black hole because it is one. The apparent tuning is just a reflection of our cosmic origins. Number 6, dark energy could be the engine driving us away from our parent. In 1998, 2 teams of astronomers studying distant supernovae made a shocking discovery. They expected to find that the expansion of the universe was slowing down due to gravity. Instead, they found the opposite. The expansion is accelerating. Something is pushing space-time apart, acting like a form of anti-gravity. This mysterious force was named dark energy. It is now believed to make up about 68% of the total energy density of the universe. We do not know what it is, but we can see its effects. It is the dominant component of the cosmos today and will become even more dominant in the future. In the standard cosmological model, dark energy is often represented by the cosmological constant, the same one that had to be so finely tuned. It is an intrinsic energy of empty space itself, but this explanation is just a label. It does not explain where this energy comes from. The baby universe hypothesis offers a potential source for this cosmic acceleration. In models where a new universe is born from a bounce inside a black hole, the bounce itself is an incredibly violent, repulsive event. The immense pressure and energy that reverse the gravitational collapse and trigger the new Big Bang could be the origin of dark energy. In this scenario, dark energy is not a property of empty space. It is a remnant of the creation event. It is the leftover push from the bounce that is still driving our universe's expansion today. The initial explosive force from the rebound was enormous, driving the early expansion of the universe. As the universe expanded and the density of matter decreased, this constant background push began to dominate over gravity, leading to the accelerated expansion we observe now. This connects a major modern mystery, dark energy, directly to the origin of the universe. It is not some new strange substance that appeared out of nowhere. It is the engine of our birth, still humming in the background. This could also explain the value of the cosmological constant. Its tiny but positive value might be determined by the mass of the parent black hole and the specific physics of the bounce. Different black holes might produce universes with different amounts of dark energy. Some theories take this even further. In certain models, the matter falling into the parent black hole could be converted into the energy that drives the expansion of the baby universe. This provides a conservation of energy across the multiverse. The energy is not created from nothing in the Big Bang. It is recycled from the parent cosmos. This view changes our picture of the future. If dark energy is a constant push, the universe will continue to accelerate its expansion forever, and galaxies will recede from one another until our own Milky Way is an isolated island in an endless dark void. This is known as the Big Freeze, or heat death, but if the baby universe theory is correct, this is not the end of the story. Within our own aging, expanding universe, new stars will form, live, and die. Some will collapse into black holes, creating new baby universes with their own big bangs and their own futures. The existence of dark energy, the very force that seems to be driving our universe towards a lonely end, might be the clearest sign that we are part of an endless cycle of cosmic birth, death, and rebirth. It is the echo of our own creation. Number 5, the imbalance of matter and antimatter is a cosmic birth defect. For every fundamental particle of matter, there exists an antiparticle with the same mass but opposite charge. A proton has a positive charge, an antiproton has a negative charge, an electron is negative, a positron is positive. When a particle and its antiparticle meet, they annihilate each other in a burst of energy. Conversely, energy can create matter, but according to the known laws of physics, it should always create equal amounts of matter and antimatter. This leads to a profound mystery. The Big Bang should have produced equal amounts of matter and antimatter. As the early universe cooled, these particles and antiparticles should have annihilated each other, leaving behind a universe filled with nothing but photons and a few leftover particles. But that is not what we see. We live in a universe made almost entirely of matter. For every billion particles of antimatter in the early universe, there were 1,000,000,001 particles of matter. That tiny surplus, 1 part in a billion, is responsible for everything we see today, every star, every galaxy, every planet. The question is, where did this asymmetry come from? Like, why the preference for matter over antimatter? This is known as the problem of baryogenesis. Russian physicist Andrei Sakharov laid out the conditions necessary for such an asymmetry to develop, but the specific mechanism within the standard model of particle physics is still unknown and highly speculative. The baby universe hypothesis offers a new arena in which this asymmetry could have been generated. The extreme conditions inside a collapsing black hole, at the moment of the bounce, involve physics far beyond what we can test in our laboratories. It is a place of unimaginable gravity, density, and temperature. In some theoretical models, the intense gravitational fields and space-time torsion present during the bounce could create a natural preference for matter over antimatter. The very fabric of space-time could be chiral or handed in this extreme environment, interacting differently with matter particles than with antimatter particles. For example, some theories that try to unite gravity with the other forces of nature, like string theory or M theory, predict the existence of new particles and interactions that are not symmetric between matter and antimatter. These interactions are usually too weak to be observed today, but could have been dominant during the fiery birth of our universe inside the parent black hole. The matter-antimatter imbalance would then be a kind of birth defect, an asymmetry imparted to our universe at the moment of its creation. It was not a random fluctuation, but a direct consequence of the physics of the bounce. The specific amount of the surplus, that 1 part in a billion difference, would be determined by the properties of the parent black hole and the fundamental laws of quantum gravity. This explanation is attractive because it takes a seemingly arbitrary feature of our universe and links it to the dynamics of its origin. It suggests that the reason we exist is due to the violent and asymmetric nature of our cosmic birth. The universe is not perfectly symmetrical because it was born from a process that was not perfectly symmetrical. The same way, a spinning object creates a vortex, the extreme physics of a black hole bounce could have created a slight preference for one type of matter over another, leaving us with the substance of our reality. Number 4, it answers the unanswerable. What came before the Big Bang? In the standard Big Bang model, the question, what came before the Big Bang, is meaningless. Since time and space themselves began at that moment, there was no before. It is like asking what is north of the North Pole. The question itself is based on a flawed premise. While this is a logically consistent answer, it is deeply unsatisfying. It places a hard limit on our scientific inquiry, an absolute beginning that we can never peer beyond. This has always been one of the biggest philosophical problems with the Big Bang Theory. It leaves us with a moment of creation, ex nihilo from nothing. Science is the study of cause and effect, yet the biggest event in our history, the creation of everything, is presented as an effect without a cause. It feels more like theology than physics. The baby universe hypothesis completely reframes the question. The question, what came before our Big Bang, suddenly has a coherent physical answer. What came before was a parent universe, a universe with its own stars, its own galaxies, and its own laws of physics, likely very similar to our own. In that universe, a massive star lived and died, its core collapsing under its own weight to form a black hole. The formation of that black hole was the event that triggered our Big Bang. Our beginning was not the beginning of everything. It was just one event in a possibly infinite chain of cosmic history. Our universe is a link in a chain, not the start of it. This removes the need for a singular, unexplained creation event. The origin of our universe is demystified. It becomes a natural process, a part of a larger cosmic ecosystem. This idea of a multiverse is not new, but many multiverse theories, like the many worlds interpretation of quantum mechanics or eternal inflation, produce an infinite number of universes with random properties. The baby universe model, particularly when combined with cosmological natural selection, provides a more structured and dynamic multiverse. It is not just a collection of random universes, it is a family tree. Universes have parents and children. There is a lineage and evolution. This also solves the beginning of time problem. And time did not begin with our Big Bang. Time is likely eternal, stretching infinitely into the past and future across this network of interconnected universes. Our time is just the time measured since our particular universe started expanding. But the process that created us existed in the timeline of our parent universe. This perspective is humbling. It suggests our entire 13.8 billion-year-old cosmos, with its hundreds of billions of galaxies, is just one small bubble in a much larger, and possibly eternal, foam of existence. Our Big Bang was not a unique moment of cosmic significance. It was a common, natural event. By providing a before, the baby universe theory brings the origin of the cosmos back into the realm of testable physical science and away from the edge of metaphysics. It replaces an absolute beginning with an ongoing process. It suggests the universe, or the multiverse, has no beginning and no end. It is a self-sustaining, self-creating system with black holes acting as the seeds for perpetual renewal. Number 3. Quantum entanglement might be a relic of our connected origin. Quantum entanglement is one of the strangest and most well-verified phenomena in physics. When two particles are created in a certain way, their fates become linked, no matter how far apart they are separated. If you measure a property of one particle like its spin, you instantly know the corresponding property of the other, even if it is on the other side of the galaxy. Einstein famously called this spooky action at a distance. The universe itself may have been born in a state of maximum entanglement. The matter and energy that formed our universe were, in the baby universe model, compressed into an infinitesimally small space inside the parent black hole. In this state, everything was in intimate contact. All the particles that would eventually form all the stars and galaxies were part of a single, unified quantum system. The big bounce that started our universe's expansion would have sent these particles flying apart. But the initial entanglement would remain. This could mean that particles on opposite sides of the universe are still linked in a spooky way, a relic of their shared origin. Some physicists have speculated that this primordial entanglement could have macroscopic effects. It could be related to the large-scale structure of the universe, the way galaxies are distributed in a cosmic web of filaments and voids. The correlations we see in the cosmic microwave background might not just be due to temperature uniformity, but also to these deep quantum connections imprinted at the moment of creation. This also provides a different lens through which to view the holographic principle. The idea that all the information in a volume of space can be encoded on its boundary, like the event horizon of a black hole, is deeply connected to entanglement. A baby universe born from a black hole would inherit this holographic property. The information content of our entire three-dimensional universe might be, in some sense, encoded on our cosmological horizon, the boundary of our observable patch. Furthermore, the concept of a wormhole or an Einstein-Rosen bridge, which is the theoretical structure connecting a black hole to a white hole, the source of a new universe, has been mathematically linked to quantum entanglement. In 2013, physicists Juan Maldacena and Leonard Susskind proposed the ER equals EPR conjecture. ER stands for Einstein-Rosen-Bridges wormholes, and EPR stands for Einstein-Podolsky-Rosen, the authors of the famous paper on entanglement. Their conjecture suggests that two entangled particles are, in a deep sense, connected by a microscopic wormhole. If this is true on a microscopic scale, it might also be true on a cosmic one. The entire universe, being born from a single quantum event, could be a massively entangled system. The interconnectedness we see in quantum mechanics might be a fundamental feature of a reality that was born from a single unified source. The spooky action at a distance is not so spooky if you consider that, at the very beginning, there was no distance. Everything was one. The baby universe hypothesis provides a physical origin for this universal state of entanglement. We are all, and everything is, connected by quantum threads that trace back to the moment of our birth inside a black hole, a moment when the distinction between individual particles dissolved into a single, unified whole. Number 2, the laws of physics themselves might be evolving. We tend to think of the laws of physics, the speed of light, the strength of gravity, the charge of an electron light as eternal and unchanging. They are the fixed rules of the game. They were set at the Big Bang, and have been the same ever since. But what if they are not? What if, like the traits of a biological species, the laws of physics can change and evolve over time? This is the most profound implication of Lee Smolin's cosmological natural selection. If universes reproduce via black holes, and if the physical constants can change slightly with each new generation, then the laws of physics are not fundamental in the way we thought. They are the contingent outcome of a long evolutionary process. You know, our universe has the laws it does for the same reason a polar bear has thick white fur. Those traits were successful in a previous environment. In our case, the environment is the multiverse, and success is defined as the ability to produce more black holes. Our universe's physical constants are not a perfect, divinely inspired set of rules. They are just a local bylaw that works very well for cosmic reproduction. This idea completely changes our search for a theory of everything. Many physicists hope to find a single elegant equation from which all the laws of nature can be derived. But if those laws are evolved, such a theory might not exist. The specific values of the constants might not be derivable from first principles at all. They might have a historical, accidental component, just like the specific shape of a giraffe's neck. Asking why the gravitational constant has the exact value it does might be like asking why a human has exactly 5 fingers. There is an evolutionary story, but not a single necessary mathematical reason. This could explain why some of the constants in our standard model of particle physics seem so random and unrelated. There are about 26 of them, and their values are not predicted by the theory they have to be measured experimentally. In an evolutionary model, these are the genes of our universe, a collection of values that worked for our ancestors. This also means that other universes in the multiverse could have different laws of physics. Some might be wildly different, unable to even form atoms. Others might be subtly different, with slightly stronger gravity or a faster speed of light. Our universe is not the only possible one. It is just one successful branch on a vast cosmic family tree. The concept of evolving laws is a radical departure from traditional physics, but it is a natural consequence of taking the baby universe idea seriously. It means that the rules governing reality are not static. They are part of the universe itself, born with it, and potentially changing with each new generation. We are not just living in an evolving universe of stars and galaxies, but in an evolving system of physical law. The search for understanding the universe is not just about finding the rules, but also about understanding how those rules came to be. Number 1. The theory is actually testable, at least in principle. A scientific theory, no matter how elegant or compelling, must be testable. It must make predictions about the world that can be verified or falsified by experiment or observation. A theory that cannot be tested is not science. It is philosophy or speculation. For a long time, the biggest criticism of the baby universe hypothesis and multiverse theories in general was that they were untestable. How could we ever hope to get information from outside our own spacetime? However, physicists like Lee Smolin and others have argued that the theory of cosmological natural selection does make some specific testable predictions about our own universe. These tests are incredibly difficult, but they are not impossible. The first prediction is a consequence of the evolutionary model. If our universe's constants had been optimized for black hole production, then any small tweak to those constants should result in a universe that produces fewer black holes. As mentioned before, astrophysicists can run computer simulations of star formation and stellar evolution in hypothetical universes with slightly different physical laws. For example, they can change the mass of the neutron or the strength of the weak nuclear force, and see how that affects the ability of the universe to create the massive stars that become black holes. Many such studies have already been done, and they generally support the idea that our universe is very good at making black holes, and that small changes make it worse. These are not definitive proofs, but they are pieces of supporting evidence. A second, more direct prediction involves the mass of neutron stars. Neutron stars are the incredibly dense remnants of stars that are not massive enough to become black holes. There is a maximum possible mass for a neutron star, beyond which it must collapse into a black hole. This is called the Tolman-Oppenheimer-Volkoff TOV limit. Its precise value depends on the poorly understood physics of matter at extreme densities. Smolin's theory predicts that nature will have tuned the laws of physics to make this limit as low as possible, to maximize the number of stars that end up as black holes rather than neutron stars. Current estimates for the TOV limit are around 2 to 2.5 solar masses. If we consistently find neutron stars that are much more massive than this, it would be evidence against the theory. If we find that the limit is indeed low, it supports the theory. A third and more speculative test involves looking for signs of our universe's birth in the cosmic microwave background. While the bounce would have smoothed out most irregularities, some models predict that it could have left a very faint, specific signature. For example, the bounce might not have been perfectly uniform, leading to a subtle asymmetry or a specific pattern of polarization in the CMB. Detecting such a signal would be incredibly challenging, requiring next-generation telescopes and painstaking analysis, but it is a concrete, observable prediction. Finally, gravitational waves could offer a window into our origins. The Laser Interferometer Gravitational Wave Observatory LIGO has opened a new way of observing the cosmos. A big bounce event would have produced a unique background of gravitational waves. If we could ever build detectors sensitive enough to pick up this primordial gravitational wave background, its specific characteristics could tell us whether our universe began with an inflationary bang or a bounce from a previous state. These tests move the baby universe hypothesis from the realm of pure speculation into potential science. The theory is not just a nice story, it has consequences for the universe we live in today, consequences we can look for. It might take decades or even centuries of technological advancement to perform these tests definitively. But the fact that a path to verification exists is what makes the idea so powerful. Galileo's observations of Jupiter's moons were a simple, testable refutation of an old worldview. In the same way, a precise measurement of a neutron star's mass or a faint pattern in the CMB could one day provide the first concrete evidence that our vast universe is just one child among many, born from a black hole in a cosmos that came before.